So we've learned how to determine the empirical formula for metal oxides, right? And the thing about the metal oxides is we took metal, we burned it, combined it with oxygen, and we figured out the empirical formula of what was produced. We're going to learn about something now called combustion analysis. It's going to be a little different. What we're going to try to figure out from this is the empirical formula of the substance that we're actually burning. Okay, so not the output, not the product, but the substance that we're burning at the beginning. And so you use a device that we've got a picture of on page 237 in the book to perform these combustion analysis experiments, right? And so you can see you've got the substance in that first section there that's being burned. And as you burn it, you've got a couple of loops, a couple of U-shaped tubes that the products go through as you're burning this. And so the first area contains hygroscopic material. Now, if you remember what hygroscopic meant I think we learned that in the previous chapter, was that hygroscopic material readily absorbs moisture, right? And so this material is going to absorb any water that's produced from your combustion analysis. And then the second substance is going to, or the second U-shaped area is going to contain material that absorbs the carbon dioxide, right? So we're talking about complete combustion experiments here, right? Where you're producing water, you're producing carbon dioxide, and by looking at the water and the carbon dioxide that was produced, we're going to be able to figure out what the empirical formula is of the substance that we're burning. All right, so let's do an example of that it involves that process so we can understand how this works. This is example 8.4 in the book, and it tells us that a chemist is burning 50 grams of an unknown substance containing only carbon and hydrogen. So in this case here, we're starting off with a substance. We don't know how much carbon we have. We don't know how much hydrogen we have, but we know that this substance only contains carbon and hydrogen. There's nothing else, right? And we're burning it in this combustion analysis. So we're going to combine this together with oxygen gas, right? And the result's going to be water, right? It's complete combustion. So we're going to get water and we're going to get CO2. And so if the chemist is burning 50 grams of this unknown substance, and when we do the combustion analysis, we collect 146.4 grams of carbon dioxide, so 146.4 grams of this, and looks like 89.9 grams of water. Then we're asked to determine the empirical formula of the substance. Okay, so how might we go about that? Well, we're going to do some things similar to the last problem we did. We are going to figure out the number of moles of carbon dioxide that's produced, and we're going to figure out the number of moles of H2O that's produced. And we do that by going to our periodic table, just like we did for the previous problem. We want to find out what the atomic mass is of CO2, so we can figure out its molar mass. And when we look at CO2 on the periodic table, C has an atomic mass of 12.01, and oxygen has an atomic mass of 16, but there are two oxygens, so we're going to multiply 16 times 2, and the result is going to be 44.01 AMU. But again, that's also the molar mass, so that many grams per mole when we're dealing with carbon dioxide. All right. Now, if we do the same thing for water, if we look that up on the periodic table, H is 1.01 as far as the atomic mass goes. So 2 times 1.01 plus 16, which is the atomic mass of oxygen. And for that one, we get 18.02 as our molar mass, right? So both of those should allow us to figure out how many moles of CO2 were produced and how many moles of H2O were produced. So 146.4 grams of carbon dioxide were produced. We multiply that times 1 mole of CO2 divided by the molar mass, which is 44.01 grams of CO2. And so our grams cancel out, and we're left with the unit of moles, and that's 3.327 moles of CO2. okay? Now, we know what we're trying to ultimately figure out is we're trying to figure out how much carbon we have and how much hydrogen we have, right? And so what we actually need to know is we need to know how many how many moles of carbon we have over here and how many moles of hydrogen we have over here. All right, so that's important for us to remember. Because there are 3.327 moles of CO2. Remember, mole is similar to dozen, right? I told you to think about the word a dozen when you think about a mole. A dozen means we have 12 of something. Well, let's think about this. Let's say this wasn't moles, all right? Let's say this was 3.327 dozen CO2, all right? Let's simplify it even further. Let's say we had 3 dozen CO2 molecules. Now, if we had 3 dozen CO2 molecules, how many, and so that means we have a C, right, bound together with 2 O's, and we've got 3 dozen of those, right, which would be 36 of those. If we've got 3 dozen, then how many actual carbon atoms do we have? Well, because each of those molecules contains 1 carbon atom, it would mean that we have 3 dozen carbon atoms, right? Now, for oxygen, that wouldn't be true because every molecule contains 2 oxygen atoms. And so instead of 3 dozen oxygen atoms, we would actually have 6 dozen, right? We'd have twice as many since every molecule contains 2 oxygen atoms, right? But we're interested in carbon, right? Because that's what's here in our unknown substance. And so just the same way that a dozen would work, right? We don't have 3 dozen. We have 3.327 moles of CO2, but that means we also have 3.327 moles of carbon atoms, all right? So let's keep that in mind, and we're going to use that fact in just a minute. Let's do the same thing for H2O. Well, when we calculate how many moles of H2O we had, we started off with 89.9 grams of H2O. We multiply that times 1 mole of H2O over the molar mass, which is 18.02 grams of H2O. Grams of H2O cancels out, and we get a value of 4.99 moles of H2O. Okay, we're interested now not in the carbon part because there's no carbon in this, right? We're interested in the hydrogen part. So how many hydrogen atoms are there in 4.99 moles of H2O? Well, there's going to be twice as many as the number of moles of H2O because every H2O molecule has 2 hydrogen atoms in it, right? So 2 times 4.99 gives us 9.98 moles of hydrogen atoms, right? All right. Well, that means that if we got 3.327 moles of carbon and 9.98 moles of hydrogen that was produced over here on this side, that's the same amount of moles that we must have had on the left side as well. All right. So we're going to use that value to determine the ratio between the hydrogen and the carbon. Now, here's what you want to do. You always want to put, when you do this, whichever value is bigger, right? This was 9.98 moles. This was 3.327 moles. The bigger value goes on top when you determine the ratio. So we're going to determine the ratio of H to C, all right? And that's going to be 9.98 moles of H divided by 3.327 moles of carbon. And that's going to give us value of 3.00. That's our ratio of hydrogen to carbon, all right? So what that means is that for every 1 hydrogen atom, there are going to be for every 1 carbon atom, there are going to be 3 hydrogen atoms, right? And so the formula for our CH compound that we started with, that we were burning at the very beginning, is going to be for every 1 C, we have 3 hydrogens, all right? So notice what I did is we're doing the ratio of H to C, and we got 3. There are 3 H's, right? 3 H's for every 1 C. It's a ratio of 3 to 1, right? You could think of this as a fraction here, right? 3 is the same as 3 over 1. So H's were what we had on top. C was what we had on the bottom. So we have 3 H's here, and we have one carbon, okay? All right, we're going to do another combustion analysis problem. This time it's going to be a little more complicated than the one we did before, and the reason why is because they're not going to tell us in this problem that the substance that we're burning only has carbon and hydrogen in it, all right? It could have oxygen. See, the output over here is H2O and CO2, and so since there's oxygen that's produced as well, there might have been oxygen in this compound also. You know, we don't know how much. We don't even know for sure that there was some there, but there might be some there. The oxygen that's over here in these products may not have completely come from the O2 here. It could have been that there was oxygen in the original substance. So we got to figure that out. And the steps we're going to take to figure that out are the same steps that we took earlier. We're going to look at we're going to find the molar mass of H2O. And using the molar mass, we're going to figure out how many moles of H2O we have. Now, when we do the calculations for that, and that's exactly what we did in the last problem, so I'm not going to repeat that. Using a molar mass for H2O of 18.02 grams per mole, we can calculate that we have 2.43 moles of H2O. Now, remember what we did in the last problem. That is not the same number as moles of hydrogen atoms we have because of this little 2 right here, because every H2O molecule has 2 hydrogen atoms in it. So this is the number of moles of H2O, but that means there's twice as many moles of hydrogen atoms. And so that when we multiply the 2 times 2.43, we get 4.91. I'm sorry, 4.86. Sorry, I was looking at the wrong number there. 4.86 moles of hydrogen. Okay. Now for the CO2, when we do the calculation for the number of moles of CO2 using 44.01 grams per mole as the molar mass of CO2, we're going to get 1.95 moles of CO2. But since there's only one carbon atom in each carbon dioxide molecule, then that means we also have 1.95 moles of carbon. Okay. So now knowing these two numbers, 4.86 and 1.95, this time we're going to have to do a step we didn't have to do the last time. Since again, we don't know, is there oxygen in this substance here, in our initial substance that we're burning? In order to figure that out, we're going to have to figure out how many grams of carbon are in the initial substance and how many grams of hydrogen. And if when we add together the grams of carbon and the grams of hydrogen, if that does not equal 75 grams, then whatever's left over must be the number of grams of oxygen that we have. Okay, so how do we do that conversion? Well, we go to the periodic table and we look and we see that carbon has an atomic mass of, what is that? Carbon has an atomic mass of 12.01. Which means the molar mass is 12.01 grams per moles. So doing that conversion here with this 1.95 moles of carbon, that's 12.01 grams per mole of carbon, right? And that's going to give us a value of 23.4 grams of carbon. Okay, that's how many grams of carbon are in this substance here, because that's how many grams of carbon we have on the right side, right? Those values have to match up. And then doing the same calculation with the hydrogen, knowing that hydrogen has a molar mass of 1.01 grams per mole, again, taking that directly from the periodic table, then doing that calculation, we're going to put 1.01 grams on top of hydrogen divided by 1 mole of hydrogen on the bottom, and that's going to give us a value of 4.91 grams of hydrogen. Now, 23.4 and 4.91 does not add up to the 75 grams that we started with the substance. So if we add these two values together, the 4.91 and the 23.4, if we add those together and then subtract them from 75 grams, we're going to get the get how much oxygen is actually in the initial substance. So let's do the math for that. It's going to be 75 grams minus the 23.4 grams minus the 4.91 grams, and that's going to give us a total of 46.7 grams of oxygen that's in the initial substance that we burned, okay? Now we've got the moles of carbon right here. We've got the moles of hydrogen right here. In order to figure out the empirical formula, we need the number of moles of every substance that's in, of every element that's in the substance that we were burning. And so we've got to find how many moles of oxygen we have. And so we look at the molar mass of oxygen, which turns out to be 16 grams per mole. So when we do the math to calculate the number of moles of oxygen, we're going to do 1 mole of oxygen is equal to 16 grams of oxygen, and punch that into our calculator, and we get a value of 2.92 moles of oxygen. Now, if you remember with our last problem, I said what you do when you're figuring out the ratio of the atoms is you always put the bigger number on the top, okay? But notice for this one, we don't just have 2 elements that are in our compound, we have 3. And so we're going to have to do 2 ratios, and we're going to put in each of those ratios, we're going to put the bigger number on top. But in both of those ratios, the number that's on the bottom, the smaller number has to be the same. Okay, so what we're going to do is, we're always going to divide by the smaller number. So we're going to say that since the smaller number is carbon, right here, right? That's the smaller number of moles. We're going to divide both the moles of hydrogen and the moles of oxygen by the moles of carbon. So we do the calculation of the ratio of, we'll first do hydrogen. Hydrogen to carbon is going to be 4.86 moles of hydrogen divided by 1.95 moles of carbon. And that math gives us a value of 2.49. All right, I'm going to round that to 2.5. Okay, a ratio of 2.5. So what that tells us is that we have 2.5 hydrogen atoms for every carbon atom. Now we know we can't have half atoms. We'll get to how we're going to fix that in just a second. All right, but we know that ratio. Now let's do the ratio of the oxygen to the carbon. So O to C. And again, we're doing oxygen to carbon and hydrogen to carbon because carbon is the smallest number. And that always has to be on the bottom of our fraction. So we're going to do 2.92, which is our moles of oxygen, divided by 1.95, again, the moles of carbon. And that's going to give us a value of 1.5. All right. Now, what did we do before? When we came up with something like this, we said that means that for every 1 carbon atom, we have 2.5 hydrogens, right? That was our number here. And for every 1 carbon atom, we have 1.5 oxygen atoms. All right, so let's write that down. For every 1 carbon, we have 2.5 hydrogens, and we have 1.5 oxygens. Now, because I know that this is a carbohydrate, it's got carbon, hydrogen, and oxygen. And I know that whenever we write the chemical formula for carbohydrates, we put the C first, then the H, and then the O. So that's why I put them in that order. If you gave me this answer in a different order, I'm not going to count that wrong, okay? But again, when you work with these compounds enough, you know what order we tend to use. But like I said before, you can't have 2.5 or you can't have 1.5 atoms. So what are we going to do? We're going to multiply through by the smallest number that we need to in order to get rid of these decimals. Okay, so to get rid of the decimals, we would multiply each of these numbers by 2. And so this becomes C2, right? Because there's an understood 1 on our C here. So multiplying that by 2 gives us 2. 2.5 times 2 is going to give us 5. So we have 5 H's. and then 1.5 times 2 is going to give us 3 O's. So this turns out to be our empirical formula for this compound. All right, pretty cool. We can find the empirical formula using combustion analysis.